Hello, ladies and gentlemen. My name is Reimann. I'm working for the company Rigaku in the team for the business development. One of my tasks is taking care about business development for the X-ray topography tools, which are developed from the company Rigaku. Today, I'm giving a presentation which has its clear focus on a non-destructive dislocation characterization and quantification of silicon carbide substrates using this X-ray topography technology. Just to give you a brief introduction in our activities, in 2021, the company Rigaku joined forces together with the well-experienced Semiconductor Institute Fraunhofer IISB in Germany, and joined forces and built up the Center of Expertise for X-ray topography. What we are doing in this joint undertaking is that we are developing together X-ray topography tools dedicated to our customer needs. We're developing measuring procedures and defect recognition and counting algorithms from, let's say, used in R&D, also for quality assurance and production. Our activity starts already at the beginning from first demo measurements, tool demonstrations, tool demos, whatever is needed until the sales and final service and support. Let's get a little bit back in the history. So on the one hand side, we have silicon, which is mostly used as the semiconductor material worldwide. Silicon has 70 years of history in development, which means currently silicon is by definition, or let's say from the specification point of view, shows zero dislocations in the material if it's grown and treated right, using the well-known Tucholsky method and all these other things. Compared to silicon carbide has only a history of roughly 30 years, and also the crystal growth method is completely different. So silicon is grown via the Tucholsky method using a small seed at melting temperature about 1420 degrees C. Silicon carbide is grown via the sublimation growth procedure with a large seed, which is placed on the bottom of a growth cell, and with a less than 30 years of history. That means currently silicon carbide substrates show typical dislocation density of roughly about 10 to the 4th per square centimeter. This is our starting point, which means we have to deal with dislocations in a semiconductor material, which needs to be recognized and counted. What is for sure is that dislocations can have in general an impact on the device yield, especially if we're talking about electrical devices, and the reliability of those kind of devices. In the silicon carbide community, or let's say if you're growing silicon carbide crystals and making wafers out of them, it turns out that we have a huge variation of different kind of quality levels. So that means nearly every substrate is a little bit different. That requires, from the industry point of view, a characterization technique, which is on the one hand side semiconductor ready, which means is applicable in semiconductor clean room fabs. It delivers reliable data with a high throughput and is of course non-destructive. Let's have a look a little bit more in detail into the different kind of relevant dislocations which occur in the silicon carbide substrate. On the left-hand side, we have the so-called threading screw dislocations, so the TSDs, and on the right-hand side, we have so-called basal plane dislocations, the BPDs. So a major difference between the two different types of defects is that threading screw dislocations are mostly nearly perpendicular with a slight tilt due to the offcut of the wafer, so slightly perpendicular to the wafer surface. The basal plane dislocations are more or less parallel, slightly tilted, to the wafer surface. So this is a complete different occurrence in the silicon carbide crystal and wafer material. Both defects have an influence on, for instance, on the performance and the lifetime of the different kind of devices like diodes or MOSFETs or bipolar devices. These kind of defects can have a detrimental impact to the gate oxide lifetime, for instance, or can also result in growth pits, causing problems during further device processing. So that means these kind of defects need to be controlled from the starting point, from the crystal growth, until the final device processing. And especially at the initial stage, these kind of defects need to be recognized and counted to make sure which kind of material quality is used in further device processing. And maybe the device defects or the defects on the substrate level can be correlated to the further device performance. Let's start with the TSDs. If we're talking about TSDs as well as BPDs, we have to start also with an old language which is used for defect recognition and defect counting. So typically in the older times, these kind of defects were visualized using etching, so chemical etching methods. There are clear drawbacks. One drawback is that if you etch a wafer with KOH etching or sodium etching, that you destroy the wafer. It's a destructive analysis method. And especially if you're talking about TEDs and TSDs, so TEDs are threading edge dislocations, you cannot really distinguish between TEDs and TSDs if you're using a standard KOH etching. So this is one challenge. There are other approaches available, but they have also different problems. Using X-ray topography, we have come to the point that it would make sense to use reflection type of X-ray topography measurements. In our approach, we're using the 008 reflex conditions. And on the right-hand side, you can see a complete topogram of 150 millimeter silicon carbide wafers. And the TSDs appear as small dark spots in the upper side topogram. And beside these kind of defects, no further other defects are visible in today's production grade material. So what does it mean? If we look on the right-hand side lower picture, that you can easily count these kind of dark spots. And using this kind of method, we are achieved already a measurement reproducibility of about 3%, which is really great, and a tool-to-tool reproducibility of about 5%. In the next slide, I would like to give you an idea about the reproducibility of our measurements. There you can see on the right-hand side a diagram which gives you the average TSD density plotted versus the wafer position. In this example, we choose 3 directly neighboring wafers, and one time measured from the silicon phase and the second time measured from the carbon phase. And you can see that the differences between the individual wafers can be easily resolved. Furthermore, we can easily distinguish between front side and back side of the wafers, and from the trend, so to say, between the data points, the distance between the different wafers can be estimated. So this is really already a great achievement in terms of reproducibility and accuracy. Another example here is on the right-hand side, again plotted a diagram which gives you the average TSD density on the wafer, again plotted versus the position from seed end to dome end for 2 different boules, where we picked a bunch of different wafers, not necessarily neighboring, and we measured only from the silicon side. And here you can see that we easily can extract the monotonic TSD density variation as it can be expected from seed end to the dome end, dependent on the tilt of dislocations, and even small differences, roughly about 1% between neighboring wafers, can be resolved, which is a great achievement. Beside measurement accuracy and reproducibility, high throughput is essential if this kind of method will be applied to industry. So typically, a full wafer map takes about 90 minutes per wafer, but there are further approaches to reduce the measurement time. An approach B, which is called grid measurement approach, can lower down the measurement time of about 30 minutes, which is 1/3 of the original measurement time. And if you use stripe measurement or at least radial weighting of the stripe measurement, you can bring down the measurement time to 23 minutes and in parallel have the same less error if compared to a full wafer measurement. This knowledge was collected together and compiled into a semi-standard M91, which is now ready for industry and gives the possibility to really a guideline or a new language to the whole community to measure threading screw dislocations in silicon carbide by using X-ray topography. Now coming to the BPDs. The BPDs, as I've already introduced in my former slide, are more or less parallel to the wafer surface. And the first question which we have to take into account is the first thing that we have to take into account is that we cannot measure the BPDs just in reflection geometry due to the in-plane Burgers vector. So that means usually the basal planes are measured in X-ray in transmission geometry. But the question is which kind of properties we need to investigate. So we can just simply count the BPDs, or the penetration points, or we have to count the BPD lengths. What is clear from literature that the volumetric density in centimeter per cubic centimeter differs strongly of a factor of 14 from the classical edge bit density. On the next slide, I've brought to you some typical examples of images which shows you different kind of densities of the BPDs, so low, medium, and high densities. And to our understanding, it's a so-called noodle salad challenge. So what kind of thing we have to detect? So that means the detection of start and end of dislocation is already challenging for low dislocated density areas. At higher densities, we have a strong overlapping that hinders clearly the differentiation between dislocations, and a discrete counting, like for TSDs, is not possible. So we have to go for a different approach. And our approach was to use a calibrated approach to obtain results consistent to KOH etching. So what is done on the one hand side, we carefully etch a bunch of wafers which show different levels of BPD densities over the full wafer area, and we do a very careful counting of the dislocation densities with a microscope, and then we correlate this kind of data with our so-called XRT value, and we obtain a calibration curve which we use to finally determine the BPD density in our material on full wafer scale. On the right hand side, you can see two comparisons of two different kind of wafer materials. On the left, you can see KOH etched wafers, and on the right hand side you can see XRT measurements, and what is easily seeable is that both results are in good agreement with our approach. And also, once the calibration curve is obtained, you can use this for each and every wafer for each and every silicon carbide supply. Also here, there's the clear credo, the faster the better for industry application. 3 years ago, we started with our standard approach, which gives a measurement time far 1.5 hours. And now we have reached the stage that you can easily measure the basal plane dislocation density on a full wafer scale for 150 millimeter wafer within 5 minutes, which is a real breakthrough in terms of defect detection on silicon carbide wafers. Furthermore, we can add that these kind of measurements are completely insensitive to lattice curvature. So that means wafers that fail due to a huge bow or curvature can easily measured with this approach. What we have obtained so far is a measurement reproducibility of about 5% and a tool-to-tool reproducibility of about 5%, or 450 basal planes per square centimeter. Again, also this approach is filled into a semi-norm, M93, for the test and quantification of basal plane dislocations with X-ray topography, and already ready for industry. Besides having a nice tool which can generate highly contrasted images to visualize dislocations, you need to have a dedicated defect analytics software, which is called the XRT Toolbox. So with the experience from the different kind of defect analysis, this is condensed into this kind of software. The software has a very fast post-processing time for less than 5 minutes for a full wafer. It's currently built for the analysis of silicon carbide wafers, and for sure can be adapted also to analyze other defects in other materials. The most important thing here is that this implemented evaluation routines is fully compatible to the already mentioned semi-standard, so that means it's ready for industry, ready to use. So in summary, I hope I could have shown you that XRT has become a major technique ready for application in industry. We have obtained a high accuracy, high reproducibility. We have built up semi-standard procedures with high throughput tools. For sure, further developments are in progress. We are looking in the direction of throughput, for instance, and other defects, and please be invited for a further discussion. At the end, I would like to thank you for your kind attention.